This question says, how much heat energy is released if 51.5 grams of oxygen are burned with plenty of methane? And then we're given the reaction, methane plus oxygen yields CO2 plus H2O. And then we have the delta H reaction of minus 892 kilojoules. So it's really important to remember that the amount matters. And methane is the major component of natural gas. And it makes perfect sense that the amount matters. So if you have a natural gas stove, right, a kitchen burner, and you put a pot of water on there, and you turn the burner on for 10 seconds, the pot of water is not going to boil, right? But if you turn it on for 10 minutes or whatever it takes, the pot of water will boil. So the time here is the amount of methane that's present. And the more methane there is, the more heat energy is given off. That's why the pot of water will boil after 10 minutes and it won't boil after 10 seconds. So the question becomes, well, how do I know how much, in this case oxygen, I have to burn, because I have plenty of methane, in order for this much energy to be released? And the answer to that is, this is the delta H of reaction. So if I do this reaction one time, this is how much heat energy is released. And I have to be able to read this reaction like a chemist. As a chemist, this says if I burn 1 mole of methane in the presence of 2 moles of oxygen, I will make 1 mole of carbon dioxide and 2 moles of water. Said another way, if I burn 2 moles of oxygen, I will release 892 kilojoules of energy. Now, let's go ahead and read the actual question again. It says, how much heat energy is released if 51.5 grams of oxygen are burned with plenty of methane? So I want to do a plan of attack here, because this is very similar to a stoichiometry problem. I want to convert from grams of oxygen to moles of oxygen, and then I want to convert to kilojoules. Okay? So if we go with the grams of oxygen, we start with 51.5 grams of oxygen times, whoops, my pen went through there, the molar mass of oxygen, remember it's diatomic, so it's 32 grams of O2 oxygen, not 16, per 1 mole of oxygen. Now we have to go to kilojoules. Well, what this means is 892 kilojoules equals how much oxygen? 2 moles of oxygen, because the delta H reaction is for this reaction, and this reaction says react 2 moles of oxygen. So we need to get moles of oxygen to go, so we put 2 moles of oxygen on the bottom, and on top we put our 892 kilojoules. And when we do that math, we get 718 kilojoules. A common question I get about this is, why isn't this negative? And it has to do with the wording of the problem. Because this says how much heat energy is released, it's looking for the magnitude, not the direction. So the truth is, if you were asked for the delta H, it would be negative 718 kilojoules. But if it's just the magnitude, how much heat energy is released, 718 kilojoules is good enough. All right, you probably wouldn't see the negative answer here on an exam or something like that, because that's a little bit tricky. All right, the next question refers to the same reaction, but it's a completely different question. How much water in grams must be formed for 5,291 kilojoules to be released? Well, let's look at the reaction with respect to water. It turns out that water has the same stoichiometric coefficient, so 892 kilojoules is equal to 2 moles of water. Okay, because it just happens to be 2, just like oxygen. Now, let's do our plan of attack. In this case, we're starting with kilojoules. We want to convert that to moles of water, and then to grams of water. So it's exactly the opposite of what we did before, so we're doing the question in both directions. So if we start with kilojoules, we're given the number of kilojoules, 5,291 kilojoules, times, okay, we want to convert this to moles of water. So we use this equality. We put the 892 kilojoules on the bottom, because we want the kilojoules to cancel out, and we put the 2 moles of water on the top. So all that dimensional analysis and stoichiometry stuff you learned before comes back again. It came back. It will come back again in the gas law chapter as well. All right, so we have the moles of water, and now we can convert it to grams by just putting the molar mass. So we put the 1 mole of water on the bottom and the 18.02 grams of water on the top. And when we do all that math, we find that there are 214 grams of water that must be formed in order to release this amount of energy. Okay, so this is essentially how you can use delta H reactions to do stoichiometry-like calculations.